So we're going to start off the last afternoon of this conference with Scott Taylor is going to talk about handle structures and additivity.
Great, thank you. As the last speaker, I'd like us all to thank Ken. So, thank you. I also want to say this was supposed to be a joint talk with my collaborator Maggie Tomova, who was unable to make it to the conference, fortunately, but she could be here. And what I thought I would do is give a survey of our work over the past decade to kind of try to convey a certain kind of perspective that we're taking on some things. And I may even give a circular Morse thing. So one of the motivating questions that has inspired our work is the question, is it possible to use non-invariants that we know are additive to study invariants that are either not additive or that we don't know are additive? I mean, if you sort of cast your mind through the various kinds of not or three-manifold invariants you know of, so you can come up with your own personal list of favorite invariants that are additive or maybe multiplicative and invariant. But then there's other invariants that aren't and that seem to behave very strangely. And for us, one of the invariant that the additive invariant that's inspiring and that we love is bridge number for knots. And a knot invariant that is not additive, and which is in some ways deeply frustrating, is tunnel number. So is there some way of using bridge number to better understand the erratic behavior of tunnel number? So I'll define that in a bit, but I'm going to kind of talk about the objects that we're going to work with. So throughout M will be a compact, connected, orientable three-manifold, and I'll eventually have to put some conditions on its boundary, but I think that's good for now. And T will be a properly embedded spatial graph, so like a finite CW complex. And you can take T to be a knot for a link if you like, and I think we have interesting things to say in that case as well. So what I'm going to assume is, just kind of simplifying assumptions, no component of boundary M is a twice punctured sphere, and no vertex of T has degree 2. Just because you can kind of absorb things in.
So how does the boundary of M have boundary?
Thinking of the feet of
You mean in the complement of T?
Yeah. So I'm going to phrase things in terms of the pair MT, and if so, here I'll draw a spatial graph just for the heck of it. If I have some surface, like there's a sphere inside, and this is a spatial graph in S3, here's a sphere. The surface will be my surfaces will be transverse to the graph, and I'll think about the points of intersection as being punctures. And so my assumption is that no component of boundary M is a sphere with exactly 2 punctures. And the rationale, this is not really a big deal because you could cap off that kind of sphere with a 3-ball containing an unknotted arc, for instance. Just like you can absorb a degree 2 vertex of the graph into an edge. So the goal is to build the pair MT using handles. And I mean, people have done this for ages. Let me tell you the kind of perspective we'll take on it. So I'm going to tell you what the 0 handles and 1 handles are. There are also 2 handles and 3 handles that are just those things with attaching regions changed. So a little bit about that. So the 0 handles come in 3 or 4 varieties. So a 3-ball. I meant to draw my graph using blue. A 3-ball containing an unknotted arc. A 3-ball containing a graph that's the cone on some number of points in the boundary. And then the last kind, this came up in one of the earlier talks. I'm just going to draw it schematically. Will have a compact orientable closed surface. And I'll thicken it. This is really what will let me work with 3 manifolds of boundary. And I can have some number of vertical arcs in there, possibly 0. So those are my 0 handles. And for this will be the negative side, and this will be the positive side there. And the boundaries of those things are all positive, and there's no negative boundary. One thing the reason I said 3 or 4 examples is that if you were to drill out the vertex and turn it into a boundary component, this 3rd example is really just an example of the 4th kind of example. Okay, so those are the 0 handles, and the 1 handles come in 2 varieties. The usual kind of 1 handle, and then a 1 handle where I also have the core of the 1 handle. 0 handles, as usual, the attaching region is empty, and the 1 handles, the attaching region is the feet. I guess maybe I should just quickly draw the 2 handles. So the 2 handles are just 1 handle's turned upside down. I do a soundtrack, I guess.
No idea what that is.
So 2 handles, we just have the other attaching region, and 3 handles are 0 handles with attaching region. The boundary plus. Okay, so
You
yeah.
don't consider parallel edge in 1 handle?
No, I don't. Just 1. Yeah. At some point, we did think about what happens if you start allowing parallel edges. It's very bad. With what I'll get to at the end of the talk, if I don't take too long, is that there are applications of this machinery to orbifolds and to group actions on three manifolds. And from an orbifold perspective, you can look at these and say, hey, people were working with these back in the these handles back in the 90s. I think sometimes they were called like orbit handles. They are, so these things arise in like an orbifold context too, which is maybe additional motivation that you don't necessarily want to make things more complicated than that. There's kind of a few things to be careful of with this kind of handle structure as opposed to the classical kind of handle structures. So if you think about trying to build your three manifold and graph pair with these handles, so first you add some zero handles, and then you add some one handles, and then you add some two handles, and then maybe you want to add some one handles again. And I didn't say it, but hopefully you were assuming it. When we attach the handles that have bits of the graph in there, we always want the endpoints to match up. And so if you notice, you can attach a one handle to a two handle. Like if this two handle was attached first, and then you attach this one handle, the one handle will come into the top of the two handle and join up. And then you're not allowed to slide your one handle off the two handle. And if you've studied like the classical handle theory from like Rourke and Sanderson or something, you know this is actually something you like do all the time in handle theory. And mostly people sort of don't even bother mentioning it anymore. But you can't necessarily slide one handles off of two handles. In this case, if you touch this kind of one handle to a two handle, you can. Okay, so to keep track of handle structures, we'll turn to Haggard splittings and related things. So I'm going to define a notion of compression body, and then we'll stack compression bodies together in much the same way as.
I have a question, excuse me. Scott,
Yeah.
hi, Jennifer.
Hi.
So are you sure that you need that second type of two handle? Since it's such a departure from the usual theory, I'm wondering whether you can actually build everything you can build using that two handle without using it. Like, is there somewhere to maybe put in an extra zero handle and an extra one handle or something? I'm trying to figure out whether you absolutely need that one, or do you just?
Yeah, if your only goal, I feel like I'm talking to these guys here. if your only goal is to build this thing, yeah, you don't need this. In fact, you don't even need that kind of one handle. But if you want to build things that have the special properties we can do things with, then yes, we do need it. There is actually kind of an interesting history here. So a few people have, so I think Petronio has handles, at some point considers handle structures like this, including this kind of one handle, but excluding this kind of two handle. Mm-hmm. But Zimmerman, actually, I think before Petronio, considered all the, basically all the handles I've listed here. And one effect of like keeping this kind of one handle but excluding this kind of two handle is you can't turn your handle structures upside down anymore.
Good point. Yeah. Mm-hmm.
Which is something that's useful to do sometimes. So.
Okay. Yeah. Thanks.
Yeah. Okay. So I'm going to define something that I completely regret the name of, but Maggie tells me it's too late to change. So I'll call this a vertex punctured compression body, and henceforth I'll abbreviate it to VPC. The name just comes from the fact that if you puncture the vertex on this kind of zero handle, you get that kind of zero handle. We did kind of feel like we needed a new name since there are so many different kinds of compression bodies out there. But whatever. Anyway, go with it. So basically, it's zero handles and one handles as usual. So for instance, let me kind of draw a kind of schematic picture of this. Maybe we have one of these product zero handles and one of these ones with a vertex. Maybe we have one that doesn't have the vertex. Maybe we have one that doesn't have any knot in it at all. Maybe there's some vertical edges there, and then maybe I attach a zero handle like so, attach a zero handle like that. My VPCs are always going to be connected. And then add some extra ones on to drive up the genus. I could even do that here. So, oh, I could maybe, well, all right, I want to do one more here. So if I attach one handle like this, you notice you get a closed loop. So you can categorize the arcs into things. So this is a vertical arc, for hopefully obvious reasons. This arc in the whole thing is what we call a ghost arc. Basically, a ghost arc is an arc that has its endpoints on the negative boundary and is disjoint from the positive boundary. This thing is a core loop. This thing is a bridge arc. So I don't need to go into the details of this too much, but if you think about it, you can see that these are basically the pieces that you'll get once you puncture the vertex. Is you get vertical arcs, you get ghost arcs, core loops, bridge arcs. And you could not, of course, not have any arcs at all, in which case you have a traditional compression body. And so we have positive boundary. And we have negative boundary. The negative boundary doesn't have to be connected, but I want the whole thing to be connected. One thing I want to point out is that in the context of studying reducible manifolds or composite knots, it can actually be useful to consider things that are not necessarily compressing disks. So for example, let me just, so if I remove 2 3 balls from a bigger 3 ball, there's a disk here that's the co-core of the one handle that joins my 2 product 0 handles together. But this disk is not a compressing disk, right? Its boundary is actually inessential in boundary plus. You can have a similar example. Sorry, I wanted this to be green. Like that, where you end up with a once punctured disk. We call this kind of thing a semi-compressing disk. Namely, a semi-compressing disk is a disk that maybe it's an unpunctured disk, has inessential boundary, but the disk is not isotopic into the surface. So this is a 3 ball minus 2 smaller 3 balls. And you can get it from S2 times I, S2 times I, one handle. So that's an example. And this kind of disk is a semi-cut disk. I think historically, things that we would call cut disks, namely once punctured disks, were called like orbifold compressing disks. Okay, so here's the definition. Rather than giving you instructions for gluing, I'll give you instructions for disassembling. So a compact, orientable surface script H inside the pair MT is a multiple VP bridge surface if the following is true. So this definition is modeled on a definition from Hayashi Shimakawa, building on a whole line of work, in particular Charlotte Thompson. Script H is the disjoint union of what we call thick surfaces and thin surfaces. And the thick surfaces have to be non-additive. You have to have at least one thick surface. You don't necessarily have to have thin surfaces. And those are, of course, components of H. When you disassemble your three-manifold graph pair along H, what you get is the union of VPCs. The thick surfaces correspond to the positive boundary. And the thin surfaces, together with the boundary of the manifold, correspond to the negative boundary. So, going back here, if I summarize this whole picture that way, what we have is maybe some this kind of picture. So we've taken these VPCs and we've glued some positive boundaries together. Those are the longer lines. We've glued some negative boundaries together, and the boundary of the manifold is part of the negative boundary. So I'm going to put one additional structure onto all these things. That will violate the spirit of the conference, but let me pause here and ask if there are any questions.
You don't consider structure.
Yeah, so at the moment, this allows for circular in position or Hagar splittings. But I'm about to tell you a structure that prevents that. So H is oriented if two things. First of all, each component has a transverse orientation. I think the fast way to say it is so that each of these VPCs is a cobordism, meaning like if this thick surface has the upward transverse orientation, then the thin surfaces are pointing out. So once you've given everything a transverse orientation, there's a dual digraph. And the second requirement is that the dual digraph is acyclic. So some of what we do works even without the oriented hypothesis on there, in which case you could do things for certain. So the dual digraph is put a vertex for each VPC and put a directed edge through every thick and thin surface. Yeah, so I think this is essentially the four complexes of Charlemagne, Schultens, and Saito.
So you're going to really say acyclic is part of the definition of being oriented?
I was afraid you'd complain about that, Ken.
I am complaining.
Yeah, sorry.
I mean, right. I mean, like, it's number one is what you need in order to actually do the circular splits. Because otherwise, you could have taken those two boundary components and smashed them together. Right?
Yeah, I apologize, but it's in print.
No.
Yeah. No, I agree.
Retracted.
Yeah, it's your retraction. Ken doesn't like it. I do actually.
VPC, very poor choice.
Very poor choice. Okay. The dual digraph as an undirected graph could have cycles. That's okay. So just like the four complex. So I'll let bold H of MT be the set of oriented multiple VP bridge surfaces. Okay. So again, building on the work of many, many people, Maggie and I defined a partial order on this set. So I guess I particularly want to say that our line of thinking goes back to Charlemagne Thompson and particularly includes Hayashi Shimakawa. And others, including people who are in the audience. If you think your name should be there, it is somewhere. Okay, so what the theorem says is that there is a partial order arrow on the set of these things. The partial order is pronounced thins 2. Such that a few things. So first of all, no matter what J you start with, there exists an H so that J thins to H and H is minimal in the post-set terminology. In other words, locally thin. And the second condition is that, or the second part of the theorem, is that locally thin H have, I'm just going to summarize it here, many good properties. So let me just say some of them, and then I'll write down the one that I want to be really relevant for the rest of the talk. So the thin surfaces are what we call C essential. So this means a few things. So the thin surfaces don't admit any compressing disk. They're incompressible. They're also what we call cut incompressible, meaning they don't allow like once punctured compressing disks. They are also not boundary parallel in the exterior of the graph. The thick surfaces are what we call SC, strongly irreducible. So you don't have any of these compressing or cut compressing or semi-compressing or semi-cut compressing disks that are disjoint and on opposite sides. And sort of a consequence of that more technical kind of thing is the following fact, which is that if this pair MT has an essential twice or thrice punctured sphere, then there is one in the collection of your thin surfaces. So just think about twice punctured spheres. That's what comes up if you're doing connected sum of knots. What this is saying is that if T was a knot that was composite, then you can detect the fact that it's composite from these locally thin bridge surfaces, multiple surfaces. And that's the key to proving things about additivity, which I'll do in the next section. But I just in the spirit of the conference, I wanted to say something about the thinning, and maybe there's something that we will notice, but I will point it out here. So here's kind of an example for Wino cycles in the dual digraph. So imagine that we have let me just call this H. Here's H times S1. Here's another copy of H. And let's say that I've removed a three ball on either side of H, or on either side of H union F. And let's say I have a bit of graph. So I have a knot coming in here, and it does a whole bunch of stuff on the inside that three ball, and then it comes around here, closes up. Does a whole bunch of stuff, and another loop that does a whole bunch of stuff there. Let's go ahead and, if you think about this as being those two brown things as being thin surfaces, so that I won't draw it, but you have other thick and thin surfaces inside those, on the other side of those brown curves. One of them, so this thins to partial order. It involves a whole bunch of moves. The main one is what's called weak reduction, which I think many folks here know, which is basically a way of turning a thick surface into two other thick surfaces and a thin surface. In the interest of time, maybe I won't spell out exactly how this works, but I'll just, for those who are interested, I will kind of point out what happens with this example. So there's a semi-cut disk right here for H, and there's a semi-cut disk right here for H with disjoint boundaries. I mean, their boundaries are inessential, so of course they're disjoint. And if you weak reduce using those green disks, what will happen is one copy of H gets pushed to the other side of this brown one, and another copy gets pushed on there, and you have F. And basically, and then like this, this F, one of the new thick surfaces is actually parallel to this F, so you can remove them. And basically what ends up happening is you've just you've just dragged this around here, you've dragged that around there. And then you can do it again, and you end up exactly where you started. So this theorem doesn't hold without the my second condition on the oriented hypothesis. The process of thinning may just never stop. On the other hand, it is kind of possible to conclude that, in fact, if you are thinning and you have a sequence that never terminates, something like this must happen.
Yeah, I mean, it's due to having this kind of reducible bits.
Right. Yeah, but I mean, reducible bits is what I'm interested in. So. Okay. All right, so part 2 of the talk is basically a strategy for studying additivity. Let me demonstrate by example. I'll just sketch the proof. So what I will prove, I want to use this machinery to prove that the quantity bridge number -1 for a knot is additive under connected sum. So this is a theorem that I think is originally due to Schubert in '54, and I would be completely remiss if I didn't draw attention to Schulten's result from '03. She gives a really elegant proof of this. And I'm certainly not claiming that, like, when you take all the details into account, our proof is better than Jennifer's. I don't necessarily think it is, but I think it's different. It's a different kind of perspective, and I think it's interesting you can get this there from the perspective. So, so if B is the bridge number of a knot in S3, then the bridge number of the connected sum of 2 knots -1 is equal to the bridge number of the first knot -1 plus the bridge number of the second knot -1. So let me sketch the proof. Well, actually, before I sketch the proof, let me make a definition. And I'll use this definition in other contexts too. So the definition is that if I have a surface inside MT, what, again, you know, I don't know if you like this term or not, but I'll call it the extent of S is the negative Euler characteristic plus the number of punctures all divided by 2. So if S is a sphere, the extent of S is equal to actually the number of punctures over 2 minus 1. If S was a bridge sphere, so a sphere dividing your knot into 2 trivial tangles, then this is bridge number -1. And then I will also have a quantity that we'll call net extent of one of these script h's, which is just the extent of the thick surfaces minus the extent of the thin surfaces. Okay, so here's the sketch proof. So, proving one direction, we could all give to our undergraduates to do. Proving the other direction is where all the interest lies. So we choose a minimal bridge sphere. Let me call it H for the connected sum. And give it a transverse orientation so that it lives in this set of multiple VP bridge surfaces. So as a schematic picture, we have bridges up here, bridges down here. There's some braid connected. Okay. We start by thinning H to a script H. That's locally thin. There exists an S. That's a thin surface. That's an essential twice punctured sphere. In other words, a sphere that realizes the fact that I have a composite knot. Just for simplicity, this works even when K1 and K2 are not prime, but just for the talk, let me say these are prime for simplicity. So the picture is something like this, potentially. We have S here. We have the knot is supposed to be blue. We have this. Something like this. And by uniqueness of prime decompositions, I have the prime decomposition of my knot back into K1 and K2. If K1 and K2 weren't composite, you actually just need to use a whole bunch of spheres and find a collection of spheres giving you prime decomposition amongst the thin surfaces. Okay, so somehow we need to keep track of the arithmetic. So what we need is that the net extent of script H is less than or equal to the net extent of H, which we pick, which is just the extent of H, which is bridge number -1. And now, so basically, the fact we need is that net extent is non-increasing under thinning. So this is one of the perspectives I wanted to advertise, which is that I think kind of historically, because of how thin position theory developed, there was this emphasis on width as an actual number. And so when people would thin, they would say, okay, take a knot of minimal width, and then you have a lot of nice properties and you do stuff. But part of the perspective I'd like to maybe encourage this possibility is that thinning is kind of akin to a hierarchy. It's a way of disassembling things. And what's important is that you know that this method actually stops. That your hierarchy actually comes to an end. And once you know that, you're free to actually consider various quantities that don't necessarily strictly decrease under thinning. So this net extent does not strictly decrease. In fact, in the setting I have right here, actually this is an equality. The quantity we use to guarantee that, to prove that first theorem I put on the board, that the thinning stops, is really, really complicated. It's highly unpleasant, and I hope to never work with it again. But, yeah. So once we know this, then the last piece we need is that the extent of S is equal to 0, because it's a twice functored sphere. And so we just split open and cap off. And in principle, this should work. The problem is, so cap. So the problem is we actually may have more than one thick or thin surface. So you might have a bunch of thick and thin surfaces, and you have the twice punctured thing here, and K1 sits there, and you have the twice punctured thing here, and K2 sits here. Cap off. But the goal is to relate it back to bridge number. And so what you need to do is actually somehow collapse all these things back to a single thick surface in each factor. And that's the last step. So I'm not getting into a lot of what I intended to talk about, but hopefully this is interesting. So the last step is to show that, so this is like H1 and this is H2, show that the net extent of H1 is bigger than or equal to the bridge number of K1 minus 1, and the same thing for K2. This uses something that's well known to Haggard splitters, which I originates with Jennifer, called amalgamation. And there are actually some kind of subtle things about amalgamation. So let me just point out an example to show that if you wanted to try to do this for higher genus bridge number, it might not work. Actually, it won't work. And the reason, here's one reason. So imagine that you have a thick surface like this. Maybe one down there. And you have a sphere right here. And you take the connect sum of a knot that lives in here, and that runs through those one handles like that. So the way amalgamation works is you're supposed to take your one handles and like just push them down to join up with the thing below it. But because you can't slide the feet of, you can't necessarily slide the feet of one handles off of two handles. When you try to extend this one handle down, you're stuck following the knot, and you have to crash into the other one handle. And you don't end up with a surface. You don't end up with a surface. You don't end up with any kind of bridge surface structure. So this is an example where you can't amalgamate. On the other hand, notice that this required genus. And this, I didn't write it in my proof here, but the thinning, if you started with a bridge sphere and you do this thinning, you always still have spheres. And so there's something that's kind of very special about having spheres and being in S3. That means that this amalgamation will work in that setting. Anyway, I have like 10 minutes left, so let me advertise some of the other things we're able to do with this. At least hopefully see the strategy for how one might prove that some invariant is additive. Right. So theorem 2 is that net extent is additive under connected sum of graphs or knots or links. So that's where and so connected sum is where, like if you have T1 and T2, showing up like that. And it is minus a half additive under trivalent vertex sum. So that's where you have like T1 and you have T2. And you join graphs together that way. So is quantity we call width. So here, so the width of H is the following thing. You take the extent of each thick surface and square it, add those up, do the same for the thin surfaces. And subtract. And the width of MT is the minimum over all the widths. This works for non-Hawking. So the reason why we kind of thought this was remarkable is, so when Dave Goodbye introduced bin position in this third century manifold theory paper, he also introduced this invariant called width that he uses to put things into bin position. And for a while, people thought width, that Goodbye's width might be additive, and there were a number of classes of things where it was supposed to be additive. But in 2013, Ryan Blair and Maggie Tomova showed that Goodbye's width is not additive. Our definition of width is actually just a very slight modification of Goodbye's definition. So let me just, okay, I have like 5 minutes left. I'll just summarize this. Happy to talk more if you want. So some additional applications. We have some theorems about tunnel number, how tunnel number behaves for knots, links, and genus 2 graphs. And then more recently, I have a paper on equivariant Hagar genus. So let me just quickly say something about this. So, Sharman and Schulten's proved that if you add together n prime knots, the total number of that composite is going to be at least n, even though it might not be the sum. And it's kind of interesting to ask whether there's a similar theorem for like vertex sums of graphs, or even connected sums of graphs. So I just want to highlight two examples. The first one is do the Mario and Makoto. So let me start with a two-bridge knot. And we turn this into a graph. I'm going to take a knotting tunnel for this, but I'm going to tie a knot into the unknotting tunnel. This is a composite theta curve. It's the connected sum of the trefoil and the figure 8 with a tunnel added to the figure 8. This thing actually has tunnel number 1. Because what happens, and it's kind of fun to play with, what happens is you can use, you can add this tunnel on and then do edge slides just on that trefoil and that tunnel to unknot the trefoil. And the red things, and the other edge also stays unknotted. But once you do that, then suddenly you have an unknotting tunnel for this thing. And like the whole thing falls apart, even though it's composite. Maggie and I have another example that I want to show you, and then I'll leave you with an open problem. So that's with the order 2 connected sum. Here's an example with order 3 connected sum. All right, drew it upside down. I was hiding. So you can see that's a theta curve that I got by vertex summing 3 different theta curves. The reason you can tell it's a vertex sum is that there is essential thrice function spheres right there. Well, it turns out that that's an unknotting tunnel. So this whole thing, that whole thing has tunnel number 1, even though it's in order of 3 connected sum. And what Maggie, all right, I can't resist stating a theorem. I don't remember what here this is. Is that if T has genus 2, meaning it's like a theta curve or a handcuff curve or a wedge of 2 circles, then the tunnel number of T is bigger than or equal to m minus 1 over 2 plus k, where m is the number of non-trivial actually, let me just say it's a little easier to say this for theta curves. So this is the number of non-trivial theta curve factors. and this is the number of non-trivial and non-1-0 not factors. So, like a core loop of a lens space is what I mean by a 1-0 not factor. So anyway, so there is a lower bound that's akin to the Charlemagne-Schulten's lower bound, but it's not right. And this example, and you can carry this on, and you'll see that that's a sharp bound. So the here's the open problem, which is to classify composite theta curves of tunnel number 1. And I should point out that this was done for order 2 connected sums by Mario and Makoto. But order 3 connect sums is still open, even though we can say some things about what the fact is. Okay, so I'll stop there.